Move on to question number 4. Alright. So here we are asked determine when a limit does not exist. So let's look at what the junior tutor proposed or attempted the solution. So the limiting value of a function f at x at point x at a is as follows. So this is just the normal kind of limit evaluation. So the expression here as follows denotes that the limiting value of the function when x approaches a. So this is correct. Step 2, if the value at the left side of the point and the value of the right side are equal, then it means that the function limit exists at that point. This is also true, but for a discontinuous function, the value at the point of discontinuity is not the same when limit approaches from both the sides, hence the value of the function is not defined at that point. Therefore, the limit of the function does not exist at a point when the function value at the left and right side do not approach. So this has to apply over here, this equation. So a plus h, which is a very small number, has to be equal to a minus x as it tends to a minus h. So a very small number to the left. So this is a little bit to the left and a little bit to the right of the value of a needs to be equal for the limit to exist. So this is the correct definition of determine when a limit exists and when a limit does not exist. So when a limit does not exist, this happens. So these are not equivalent. So let's write out that, because that's the main answer for this question. So the limit of x to the a plus h is just some very small number of f at x, does not equal to the limit of f at x as x tends to a minus h. Okay, so let's say we had the following plane. So we have x and we have y. So we have some function, let's say f at x, and we have, let's say this is point x equals to 3. So we know for this function at x as it tends to a, let's say a is 3 plus h, so a little bit to the right of this function. As you go into this point, you're going to get, let's say, 2. So y equals 2. Similarly, when you come from the left of the function, so as 3 minus a tiny bit, so let's say 0.001, so 3 minus a very small number. So if you're coming from the left side, you also end up with y equals 2. So this, so the limit does exist in this scenario. So let's think of a scenario when the limit does not exist. So I'll erase this and I'll redraw a different function. So we have, let's say this, and then we have something like that. So this is f at x function, but there's a discontinuity at this point. So if we were to look at this function, let's evaluate for the left side. So as x tends to a, which is 3 in this scenario, so we'll say a equals 3. As x tends to a from the right side, so plus h is a little bit to the right, or plus some very small number. So as we're coming from the right side, we'll get, let's say, y equals to 4. And as we come, as x tends to a minus h, so we're coming from the left side over here, we'll get y equals 2. So we know that 4 does not equal 2, therefore the limit does not exist in this scenario and in this example of the function that we drew out here. So here some similar problems are proposed. So for f at x, x squared, so this is kind of doing the taking the limit kind of in a longer way. So they substitute here. They're taking the limit by first principle. So this is the way to do it, by first principle. So let's say for some function x squared, we're trying to think of the limit as x goes to 0. So they substitute 0 in here, and they're left with, no, sorry, yes, they substitute 0 in here, and they're left with negative h. They evaluate for negative h, and they end up with h squared for the right side. So they're taking the limit on the right side. So they did the limit with the first principles. And then for this example, they're doing the limit on the left side, and they end up with h squared. So h squared is equal to h squared. Therefore, the limit does exist for x equals to 0. And then similarly for this is another example, and we end up with negative h. So here we don't end up with the same limit. So we have the limit here, so we have substitute negative h, and then we end up h cubed and negative h cubed, so they're not equal, and the limit does not exist at x equals to 0 for the function x cubed. So those are the kind of two examples of where and I've provided like two other examples from a visual perspective of a graph of where the limit exists and when the limit does not exist. So this answer is correct. So correct answer, great job, and we'll mark this as correct.